All right, welcome. So in the last video, we took a look at our first example of a deterministic finite automata. And in this video, I want to make that more formal by looking at the formal mathematical definitions of that same machine. So just as a quick refresher, let's remind ourselves that last time we defined our deterministic finite automata using a diagram like this, a diagram of states and transitions labeled by input characters, as well as a few other parts like the input state and the accept states of the machine. But this diagram, at least for our human purposes, fully represents what the DFA is, the deterministic finite automata. And usually when we're working with DFAs as humans, that's, we are humans, so we usually are working as humans. We like it in this visually represented format because it's easier for our brains to understand what's going on, to track the processing of symbols and so on. So typically when we're working with them, we're going to be using them in this format. But if we wanted to implement these machines in some way in in the computer, we need a more formal representation of them. And that's where mathematics comes in, where we can use some of the tools that we have from mathematics to create formal definitions that can then be manipulated, maybe even automatically by a computer to process these types of machines. So let's go and take a look. What do we need to create a formal definition of a deterministic finite automata? So this is a pretty standard definition of a DFA. Here we're going to start out by saying, well, a DFA is a five tuple or a five tuple. What is a five tuple? Well, in mathematics, we have this idea that we can place things, or in general sets is what we're dealing with here, but maybe numbers into a list or a structure that keeps them in maybe with a certain number of positions. A very common tuple that you might be familiar with is a pair or a triple. We use pairs of numbers to represent x, y coordinates in a two-dimensional space, or we use triples of numbers, x, y, z coordinates in a three-dimensional space. Or if you know a little bit about, say, colors represented in on the machine, in the computer, we might represent colors with three numbers, a three tuple, red, green, and blue, or perhaps a four tuple, red, green, blue, and transparency and alpha value. These are all examples of what a tuple is, and in this case we're just saying that we're going to use this same mathematical structure that we've been borrowing in other parts of mathematics to define what a DFA is. And in this case, we're saying a DFA is going to be a five tuple, meaning that there's going to be five pieces inside of that structure that we've created. And I'm sort of hinting that we've got this structure. The structure is like a set. It's not, a tuple is not a set, because there's something important about a tuple that is not important in sets, which is the order matters. So in this case, we say this is a five tuple. When we put the q in the first place, that's important. The first place will be the q always in our understanding of a DFA, and then the sigma and so on. Well, let's go and take a look at what are these five pieces of the deterministic finite automata. The first one, Q, is a finite set of states. So, well, we saw that in our diagram. We were using sort of circles or nodes to represent the states. And this is just saying that, okay, we need to formally define what those sets of states are. What is this set then? It's a set of states. Well, usually in our formalism, this is just a set of labels or names of those states. So a very common way for us to just label or name our states is just state 0, state 1, state 2, state 3, and so on, whatever order they happen to be inside that structure. In this case, we're calling it a set, but maybe it's a list that we're using to represent it. Then we've got our sigma, which is also another set. It's a finite set, but in this case, it's an alphabet. And remember, the differences here are only the purposes that we put them to. We might have the exact same symbols in our sigma that we had in our state. So for instance, our states might be state 0 and state 1, like we saw in our example. And then we might also have an alphabet that just has zeros and ones. So technically these states might, or these sets might be exactly the same thing, but the purpose to which we are putting those sets is different. Q are labels of states. Sigma are labels of symbols. And so keeping those purposes separate for us is all that we need to do, even if these sets ended up, by accident being very similar or the same. Okay, so those parts maybe make sense. We have states, we have some symbols we need to process. And now we've got this delta, and delta is actually probably the most complicated piece of the deterministic finite automata. It's actually pretty easy to understand once we know what its purpose is. It's the transition function. So if we've got our states defined already, we also need to define our transitions, right? So what is a transition in a formal sense? Well, what we've got here is we've got this delta. This mathematical structure here is defining a function. This is how we define a function, and I guess that's what it's telling us it is here too. It's a transition function. So what do functions do? Functions take some kind of input and map them to some kind of output. So here what we're saying is the input is the cross product of these two sets. What's the cross product again? Well, this is where we would pair up a state with an input. So basically what this is saying is, given some state that you might be in and some input symbol that you might be processing, tell us what the next state is that we will be in. That's what the transition function tells us to do. It tells us how to transition from one state, the start state, to a new state given some input character that we're processing. So that's all this is a very simple function. It takes two inputs, a state and a character, and it outputs another state, potentially the same state if the transition doesn't change states, but any state could be the possible output of this transition function. All right, that pretty much defines the whole machine, except there are just a few extra bits we need to make sure that it's going to do what we want, process symbols, that is, process an input string. First, we need somewhere to start. So pick some member of the states, and that will be our start state. And we typically just call that one Q0. Remember our set of states up here, I said maybe it would just be 0, 1, 2, 3. Well, sometimes we call it Q sub 0, Q sub 1, Q sub 2, and so on. Those are our states, and then by default we usually just make the first one the start state. If we're going to list them all out there, just put the start state in there first. That's just a common convention. It's not necessary, but in step 4 here, in this part of the fourth component of the tuple, we will just state the start state. And again, very commonly we just default to Q0, but maybe you've designed some machine, maybe you designed it out of some other machine that already had names for their states. You might have a different name there. That's all we're putting here is the name of the start state. And then same thing for the accept states or final states. So which states of the machine will cause us to accept the input if we end or terminate our processing in that state. We need to highlight those states somehow. Notice there's a subtlety or a difference here. There's only ever going to be one start state. So this Q0 is an element of the set of states. It's one of the elements. Whereas here we're saying F is a subset, meaning the number of accept states, it potentially could be all the states. If it's all the states, that means we accept every string, so that's kind of a little bit silly. It certainly can be more than a single state. That's sort of what I'm trying to emphasize here, is that our F could potentially be 4 or 5 different states, whatever it might be for that particular machine. So what we've got here is we've just highlighted what we mean when we say a deterministic finite automata in a more formal sense. It is very rare for us as humans to want to write things down in this very formal sense unless we are implementing it inside a machine somehow and we want our machine to understand what we're talking about, in which case all of these details are necessary for stating it for the machine. All right, now that we have this idea of a formal deterministic finite automata, we can now expand on it and start defining some of the processes that we will be performing on the deterministic finite automata. In particular, we want to define computation, or how it computes. Remember, the purpose of this series is to study models of computation, or the theory of computation. So we're trying to define what computation means in some very formal and structured way. So that's what we're getting at here. So let's look at the 3 different components of the computation. The first is we're going to do some initialization. I've already highlighted this both in our introduction last video, but also just discussing the parts. The start state, Q0, is where we begin processing. It's the initial state that we start off in. Then we were going to do our computation, which is sort of a loop or an iteration. Okay, what it's going to say here is if we're in some particular state Q, and we're processing some particular symbol or character sigma. So I should be clear here, this is a lowercase sigma, and we're just using that as to represent some character in our alphabet. Then we're going to use that transition function delta. We're going to plug in the Q, the state we're in. We're going to plug in the symbol, the one that we're processing, and we're going to use that to figure out what the next state is. So what computation is doing is just an iteration of applying this rule. So if we're in a state and we still have a symbol to process, we'll figure out the next state. Then we'll apply this again. What's the next symbol we process? Again, find the next state. We'll keep doing that until there are no more symbols to process, in which case we will end in the termination case. Once all the characters are processed, then we check what state we're in. The state we're in, we'll call it Q. If it happens to be in the set of final states or accepting states, then we accept. Otherwise, we reject. And again, this is just formalizing that definition that we looked at last day. So let's take these ideas and try and use that simple example machine that we have here and describe it formally as we might for a machine or in mathematics. So we might give this machine a name, and I mentioned this last day. We might call it M or M1, giving it a name to highlight it as a formal structure. And then we need to label its pieces. And so here I've given them the same names as we used in our formal definition. That's just by convention and convenience. I'm going to say, what is my set of Q? Well, I didn't label them up here, which is which, but I could write a little Q0 in here and a Q1 in there if I wanted to make it clear. But these are our two states, Q0 and Q1. Our input alphabet sigma is stated here as just the binary alphabet 0, 1. That's clear from our diagram as well. We have transitions leaving with zeros, and we have transitions leaving with ones, and that's the only symbols we see there. Which state is the start state? Well, again, we hadn't labeled these Q0, Q1, but if we had written those in there, we can see, yeah, the input arrow here is starting at Q0, so Q0 is the start state. And again, if by convention you have just default by naming your or labeling your state Q0 for the start state, this part just happens for free then. If you've already got that convention in, everyone knows that Q0 is the start state. Then finally, our final set, our set of accepting states here, is also just Q0, but notice the difference in how I've got these represented. This is just stating the state, whereas this is stating a set containing that state. And why was that? Well, in our formal definition, let's just go back. We see that it was, remember, it was that subset definition here. So this set F has to be a set, and that's why we put the curly braces around it, even though there's only one element in there or one state inside there. Okay. Finally, the transition function delta. Now, how do you want to display delta? Having a diagram to display it is usually the best way for humans. That's why we like to have it that way. Writing it as a table works as well, but it's just usually not as easy for our human brains to sort of realize what that means. But for a computer, this is perfect. I'm in state Q0. I'm processing a 0, look up in the table, there it is, that's my next state. Do it again, do it again, do it again. It turns the computation into just a bunch of table lookups on this transition table, and that can be very convenient inside of a machine. Okay, so now let's get started with just thinking again in a very formal or abstract way. While we're probably going to be looking at specific DFAs with specific inputs and asking questions, does this DFA accept this input? We can also talk about it in a very abstract way. So let's for the moment start with, let's just assume we have some machine M defined here as the 5 tuple for a DFA, so we know that this is a DFA. Okay, now I've drawn it up here kind of abstractly. I didn't put any of the transitions in there, and I maybe have left out some potential states as well. I've just tried to highlight what might be a general looking DFA. We've got some input, we've got a bunch of states, some of them are accepting states, and there's some transitions that I'm agnostic about at the moment. Now, the other thing this diagram has is it's showing our input, W, that we're going to show as sort of coming in through this input state to begin processing. And here I want to be very strict about what W is too. W is going to be one of our input strings. But when we're processing it, we don't process the whole string at once. We process it one character at a time. So it's very convenient for us to list it and give it some names, maybe W1, W2, etc., up to Wn of, we can say each Wi is from sigma, meaning each one is an element of our alphabet, or we can say this whole string is from sigma star. That's another way of saying the exact same thing. So this is sort of a simple setup. Say we've got a machine, and say we've got a string, and now we can start talking about, processing that string in that machine in some way. And now we can define formally, given the idea that we already have of computation, our formal definition of the machine, and so on, what we actually mean when we say M accepts W. So for some DFA M, that it accepts the string W. What does that mean? Well, that means by definition, if there is some sequence of states, we give that sequence of states a name. We usually call it a computation. And that sequence of states here, I've changed them to be labeled with R instead of Q because I don't want us to confuse ourselves. Q is usually the actual names of these states, like this might be Q0, this is Q1, this is Q2, Q3, and Q4, whereas R0, R1 is more of a sequence of these states. We might start at Q0 and then go to Q1, but then we might go back to Q0 and so on. So I didn't want to use the Qs as my labels here to confuse us. I'm going to use R instead, to keep in mind that that first one, R0, well, that one's probably Q0, but the next one is not necessarily going to be Q1. It could be Q3, or it could be Q0 again. It might, you might have a self loop. So here we're just highlighting, we don't know which state these are, but these are all states in some order, some sequence, okay, starting at the 0th one and going up to the nth one, all right? Now, what's important, if this is really a computation of our machine M on this string W, there are some important things that we have to do. First of all, we need to start in the start state. So this is not a computation if we started in some arbitrary other state. That it's something, but it's not a computation, because computations, when we initialize, we saw that in our initialization phase, they start in the start state. So that's that first one there. Our computation is only an official computation if we start in the start state. Okay, let's look at this next one here. It's got a little bit of formal math in there, so we want to make sure we understand what it means. It's saying here that if you're in state Ri, whichever one that is of this sequence, and you're processing symbol Wi plus 1, maybe I'll come back to those indexes here in a second, then we should, after processing that, we should arrive at the next state in the sequence. So let's maybe just think about this for the very first instance here. So let's pick a case where I, is 0, meaning our I here will be R0, our first one, okay? And then our W here, notice we've got it on I plus 1. That means we will be processing the string element W1. Well, if you notice in our setup, let's just go quickly back. Oops. We started at 1 here on purpose. So W started with 1 so that we can, you'll notice there's going to be exactly one more state than there is symbols to process, because each symbol is going to move us to a new state. So we're going to end up in one extra state. So that's where the plus 1 is going to be coming in. And you'll notice when we started in R0, the first symbol that we will process will be W1, and that should arrive us in the next state, whatever state R1 will be. And then we can reapply this, because this says this particular property needs to hold for all of our I between 0 and n minus 1. So we just looked at it for 0. Let's look at n minus 1. Well, n minus 1 will say if you're in the second to last state in this computation, and you're processing the last symbol now that would be Wn, then you will arrive in state Rn, which would be the last state. So all this property 2 is saying is as we move from state to state, we need to make sure that we're following that transition function. We're not leaping from one state to another where there is no transition between them, or we're not following transitions labeled with the wrong symbol. Okay. And then perhaps the only thing that we need to add at the end, remember this is a definition of what it means to accept W. Then at the end we could say, well, we end up in that last state we're in Rn has to be one of the ones that is the final state or an accepting state. Okay. Now notice this is a definition of what it means to accept W, but we could also make a definition of what it means to reject W, and the exact same thing would be true, except the last condition here, we would just need to say not in F, put a little slash in there, not an element of F, and now we've got a definition of what it means to reject W. Okay, although it is also very common in deterministic finite automatas to merely just say that M rejects W if it doesn't accept W. Okay, so since we already have a definition of what it means to accept W, then if it does accept, we know it doesn't reject, and if it doesn't accept, that's the definition of rejection as far as deterministic finite automatas go. And I say that as far as deterministic finite automatas go, we can make this partly because of the word deterministic that's in there, and I might highlight that a little bit more later, okay, when we start talking about complement languages and so on. But this is not going to be true for all of our models of computation, that we can just say that if it doesn't accept it, then it must reject it. Okay, that's true for our DFAs, but it is not true for other models we will look at in the future. Okay, so we can continue. We can now talk about languages that are associated with the machine. In this previous definition, we were relating machines M to specific strings. We can say this machine accepts this string, but with that definition now, we can now say, hey, what is the set of all of the strings that are accepted by W? In fact, we can see this definition right here says, let's define this language L to be all the strings W. I'm agnostic what the alphabet is here, but we could, if we want to be a little more formal, we could say W out of sigma star with some alphabet that we've previously accepted. But here it's saying all strings W from some possible sigma star such that M accepts W. So only the strings W that are accepted by this machine. We will usually call this the language of M. So we've got this nice sort of denotation here of L of M saying this is the language of the machine. And we will say that a machine M recognizes a language L if this is true, if the language of the machine is equal to L. Okay, that's sort of a straightforward definition. You'll notice we're using the word recognizes here. For DFAs, we sometimes also say accepts. So we might say M accepts L, accepts the language, which is a little bit of a category error, right? Remember, machines accept strings. They don't accept sets of strings, although we're just sort of transitioning that idea a little bit further down the road. That's one of the reasons why we use the term recognizes here instead of accepts, because we just want to make sure that we're super clear between those two distinctions. M accepts strings, machines accept strings, and they recognize languages. So we're just going to use a different term there to keep those ideas clear in our head. While I say that, I'll remind you one more time, with DFAs, we sometimes use accepts for both of these definitions. Okay, finally, and this is really where we're getting at in this first maybe unit of this series, is we're talking about a set of languages that we're going to call the regular languages. Okay, and we've now got our very first definition of what a regular language is. Any language, L, we will call it regular if it is equal to the language of some deterministic finite automata M. So what we are saying here is if you can make a DFA, a deterministic finite automata, that accepts this language, see I just did it, that recognizes this language L, then we will call that language regular. Otherwise, it's non-regular. There are other languages that cannot be accepted by a deterministic finite automata. We'll see that in a couple videos from now. But the ones that can be, we'll call them regular. Okay, so that's all I wanted for this video. So thanks a lot for watching, and we'll see you in that next video.